Well, thank you, Sam, for those over-flattering comments. And I'm sorry, you didn't mention about me being late for lectures and things like that. I want to talk about, well, what you see on the screen there. We'll just, that's comes a little bit later. But eventually I shall talk about the pattern which you see in the front of a building, the paving there, and I want to explain how that came about and what it's all about. But before getting to that, I want to make some more general comments, first about crystal symmetries, and then about non-crystal symmetries. So these things are, I assume, very familiar to people, that you can have a plane pattern which has a translational symmetry, so you can slide it along in some way and it's the same as it was before, and in addition to that has some rotational symmetry. Now there's a theorem, a very ancient theorem I think, which the only rotational symmetries you can have will be twofold, threefold, fourfold and sixfold, and just to illustrate those different symmetries we have them here. If you have a parallelogram and a pattern of them arranged like this, then about the center of that you're going to have a twofold symmetry, rotation through 180 degrees sends it into itself. Equilateral triangles, again take the center of one of the triangles, then you can rotate the whole pattern into itself 120 degrees, so it's 3 times and you're back to where you start. Fourfold, the very familiar square pattern, and sixfold hexagons. Now these are all very familiar. Why are they the only ones? Well, there are various ways you can prove that. One of the simplest is as follows. Let me just get this stuff working here. Suppose you have some pattern which has both a rotational symmetry and a translational symmetry, and we'll suppose they're discrete points which don't sort of crowd in infinitesimally close to each other, something like that. So we'll have a set of points on the plane, and I'm going to suppose that I've found a point about which the pattern has a symmetry which is one of these symmetries. So n is an n-fold symmetry, so if you rotate through 360 degrees over n, the pattern will go into itself. So that's a point in the plane with that property. And here's another one, and I'm going to choose those as close as possible. So let's find somewhere where I find 2 such symmetry points. If there's one, there's going to be another because it's got a translational symmetry, so you move this along somewhere, and there'll be another point about which it has rotational symmetry, and we're going to find 2 which are as close as they can be. Now I rotate this one about that one by the symmetry, 360 over n, and then that, since the pattern is the same when you rotate through that, that also must be an n-fold symmetry point. Then I look at this one and I rotate in the opposite direction, this one, and so that one must be an n-fold symmetry point, and you see those are closer together, which contradicts these 2 being as close as possible, with the only exceptions being, well, maybe they're not closer together, which would be the case if n equals 2, then of course they're not. N equals 3, they're not either. N equals 4, they're exactly the same distance. N equals 6, you get away with it because they coincide. And so those are the only possibilities. If you have n equals 5, you can see they're obviously closer here. If n were larger than 6, they'd cross over, but they'd still be closer together. It'd be more like that picture. Okay, so that's the proof. Really very simple, not much. You can understand that pretty reasonably, I hope. Now, what about this pattern? Well, it has a look as though it's both symmetrical in the sense you can translate it and it goes into itself, and 5-fold rotational symmetries. A lot of these stars, pentagons, and things like that. In fact, both those statements are almost true. So this pattern could be extended to infinity, and I'll show you the way you can do that. Extended to infinity, and we have the property that if you give me any percentage less than 100%, say 99.9%, then I would be able to find a way of sliding that pattern along itself, a translational symmetry, so that it goes into itself to 99.9%. That is to say, of the line segments, 99.9 of them would be in exactly the same place as before, and only 1% would be different. And you might say, no, I want it better than that. How about 99.99%? So I say, okay, yeah, I can do that too. And I find another translation, and it will agree to 99.9%. And also, I should say rotation. I can find points about which it will rotate, and the symmetry in the first case would have been 99%, secondly 99.9%. And you might say, well, no, I meant 99.99, 9999, whatever you like. There will be a translation and a rotation of this pattern, fivefold rotational symmetry and a translational symmetry to that precision. So it's almost in that sense. Never quite exactly 100%, but anything slightly short of 100%, yes, you can find it. Well, now you might go back to the original argument and say, well, what goes wrong with the argument? Let's take it so that we're looking at not exactly symmetric points, but we're looking at points which are has the symmetry to 99.9% or something. The thing is that if those are 99.9% points, these ones are likely to lose just a little bit of symmetry, because this one's only 99.9, that'll probably be 99.8 around. So you lose just slightly, they'll get me closer, but you'll have lost just a little bit of the symmetry, the precision. The precision will be slightly less, and you keep doing that, and of course by the time you've got down to the size of the pentagons here, you will have lost all the precision. So you can see that it slips through the proof. That's one, and a nice illustration is why when you give a proof of something, you really mean what you say. It's got to be, the statement has to be exactly what you say. If it's only approximately, you may find that there are loopholes, and this is a good example of that. Now, let me tell you how this pattern is constructed. It's very simple in principle. Let's take a regular pentagon, and what I'm going to do is I'm going to subdivide that pentagon into 6 smaller ones which almost fill it. So I can find out where this one is by joining those 2 points, if you like, and that tells you where that line is. So if I join non-adjacent points, I can see where that central pentagon is, and then I join those, and I can find those lines, and so on. So I find that there are 6 regular pentagons which almost fill that pentagon. Now what I'm going to do is to blow this up to the scale so that this one in the middle is now the same scale as that one, and then do it again. Blow it up, do it again. Okay? Now if I think I've got to, yes, here we are. If I do that here to this picture, then this pentagon, that's the big pentagon that was that one, and that pentagon there was that one. Where are we? That one, say. And then I subdivide these ones, and you see there's a little gap in the middle there, which is a bit of a nuisance. Never mind, we're almost there. But what I'm going to do now is imagine that we've subdivided again, and then this one will be subdivided, so there'll be a little triangle pointing in there, a little triangle pointing out there, and I'll have a sort of spiky rhombus the next time round, and it'll look like that. So this is this big pentagon there, well, it's almost off the picture here, but say that one there has now become this one, and so on. And there's my spiky rhombus in the middle, and I find that there's exactly room for another one of these pentagons down there. I still have 2 gaps. This, well, I call that a pentacle. If the lines had gone through each other, it's what people call a pentagram. But this is a pentacle. It goes in and out like that. Okay, it's a star shape. And the other one, well, I call that a jester's cap. I think that's one way of describing it. There's the jester, if you like. Okay. Okay, so we're going to keep doing that. Blow it up again. The next time, the pentacle will go little spikes like that. And the nice thing about it is that I can always just find room for pentagons. You see, if I take the pentacle and I put the spikes on, the next stage where I subdivide all these, there's little spikes sticking out there. I have another pentacle in the middle and 5 more jester's caps. And with the jester's cap here, the other way up, but never mind, it's that jester's cap there. I find 3 pentagons, 1 pentacle, and 3 jester's caps. And with the rhombus, 1 pentagon, 1 pentacle, and 1 jester's cap. So I don't have any new shapes. So each time I can blow it up and subdivide the ones I had before according to this pattern. There's only one little thing that might worry you here, at least might not, but it's more likely to worry you, I think, if you know, mathematicians like to worry about things like this when they don't need to. There's an ambiguity here. You see, this could have been done the other way up. And you say, well, okay, do it one way or the other. No, I have a rule which makes precise which way I do that. And what is that rule? Well, I'm going to adopt the following rule. Looks a bit funny here. I'm just telling you this, but it's not hard to see, that wherever you find one of these spiky rhombuses, that pentagon, either on one side or that rhombus, I should say, spiky rhombus, one side or the other, you will find this pattern. And this pattern, you look over there and see where that one is. If it's not on this side, you'll find it on the other side. And then there's a little rhombus in the middle, and the argument is that whichever way we do this is governed by where that pentagon is. So you take a symmetry about the major transverse, what do you call it, diagonal of this rhombus here, and this thing flips over a mirror symmetry about that, and that tells you where that pentagon goes. So if this one is down there, that one's down. If it were up there, that one would be up. That's the correct rule. That one's wrong. Now, why didn't I say this is the correct rule and that one's wrong? Well, there's a good reason for that. That is that next time when I subdivide, the thing in the middle is going to be ambiguous, depending on which way you look. Whereas if you take this rule, it's consistent all the way through. Okay. Well, that's what you do. And if you do that, you get a pattern like this. Well, let's do it. Okay, I'm going to start with a nice big pentagon there. And then I'm going to subdivide that according to the rules I've just been giving you.
Can you turn the volume up, please?
Do I just shout, or is there a way of doing it with... Oh, it's down there. Oh, another one. It's not going to interfere with the other ones.
No,
it makes awful squawks and things like that. Good. If it squawks, I'll hurriedly take one out of the pocket. Can you hear me now? Yes. Good. Okay, so that's the pentagon before. I subdivide that. There we go. Just according to the rules I was giving you. And then I subdivide that. There we go. Now, you see there would have been this little ambiguity possibly here, because there's that rhombus, and I look to see where should I put the pentagon. Well, I look around and I say there is that pattern of pentagons, which I warned you would be able to find, and I look at that one's over there, has to be there, and therefore this one's down there. Okay, so that's satisfying the rules, and then next time do it once more and I get the pattern that we had before. Okay? So that tells you how it's built. It's got a hierarchical construction. Now I'm going to whip those away, and just to confuse you a bit, I'm turning it upside down. Now, where was that original big pentagon? It's not so easy to find. In fact, each time I have to figure it out all over again. The point about this is that it has a uniformity that's not so obviously hierarchical. It does have a hierarchical construction, but it's really something much more regular than that. It has a highly regular structure, and the hierarchical nature is not at all obvious. In fact, it has various properties. I'll point out a few of these. For example, you see here you have a regular decagon, 10-sided figure. There's another one. And every time when you find one of these regular decagons, it's always subdivided in the same way: 3 pentagons, 2 rhombuses, and 1 pentacle, one jester's cap. Okay, and every time you find one of these, it's always surrounded by a ring of 10 pentagons. There you are. Here's another one. Always a ring of 10 pentagons, wherever it is. Sometimes these things overlap, like here. You've got 2 of them overlapping, another one there. Whenever that happens, you still find your ring of 10 pentagons. They just go quite happily through each other. And it has that very nice property. Other things which are very evident to me just when I stand here is that if I take any line on the picture, I can put a ruler against it, say any line in the picture, it will keep on going right across the picture with the same density of lines all the way up. So if you imagined suppose you had a field of corn and there was one growing at each point, vertex of this pattern, and you drive past in the car and you look at it, they'll all line up at some point and then they'll all line up again. You say, oh, that's a nice regular pattern. Well, it's one of these things maybe. At least you'd be lucky to find a farmer who'd do that, but never mind. Anyway, I just wanted to indicate that there is a lot of structure, there are a lot of features which are not at all evident from the hierarchical construction. And for example, now we have this 10-sided one in the middle here with its ring of pentagons. But in this case, you also find right the way around it a nice ring where you have rhombus, pentagon, rhombus, pentagon, rhombus, pentagon, all the way around. 10 rhombuses and pentagons alternating. And you'll find those all over the place. Okay. Now, I want to say something else about these patterns, and that is there was a problem originally to do with tiling plane with squares with colored edges, and you had different squares with different arrangements of colors, and you had to match the colors. And the question that was raised by a Chinese-American mathematician called Hai Wang, could you find a computer program which will answer yes or no, given these sets of colorings, finite set of these squares, yes or no, can you tile the entire plane with these colored squares? And he came to the conclusion that yes, there would be an algorithm for doing that, a computer program for doing that, if it were the case that for any set of colored squares, if it did tile the plane, you could be sure that it would tile the plane in a periodic way. Well, his student, Robert Berger, thought about this problem and eventually proved that there was no computer program for solving the tiling problem of this kind. And therefore, as part of his argument, in fact, he produced a set of, I think it was originally 20,426 different colored squares. He then got it down to about 100, and then Raphael Robinson got it down to about 6. And he had a way of making it into a jigsaw puzzle, rather badly drawn here, but that's what it is. You can see the squares on this piece of paper, but that's not got the designs on them. You have to fit these together, and the only way you can do it is non-periodically. So that was made it consistent that there was no computer program for solving the tiling problem with these colored squares, and the fact that there are shapes which will tile only non-periodically. Well, I was visited in the old Mathematical Institute by an American mathematician, Simon Cochin, and he was describing these things to me, and he said that Raphael Robinson was somebody who liked to get the number down as small as possible, and so he told me there were 6. And I said, well, I think I can do it with 5. And my 5 will look completely different from his. In fact, what I was actually doing was with 6. Now, those 6, you see, are actually the same, basically, as this pattern. However, the pentagons are divided into 3 classes, depending upon, well, as with this one, we have the pentagon surrounded by 5 others. Here we have it only 3, and here we have, where's another one? Only 2 here. So either 2, 3, or 5, and I'm going to make those different, and then I make it into a jigsaw puzzle where these are that's the 5, that's the 2, the 3, and that's the 2 one. And just to show you what's going on, I'll color these so that the 5 one is the orange one, and you can see what goes on. Here we go. But you see, that's still 6, like Raphael Robinson, 6. But there you are. So if you imagine the colored ones are different and they have a matching rule, according to those little knobs and notches which I just showed you, then the point is that you force that kind of pattern which I've been describing. It does have this hierarchical arrangement, but I'm not saying do it that way. I'm saying do it any way you can where you make the notches and the knobs fit together. And the only way you can do it is in the sort of arrangement which I just showed you. Now, the reason I said I thought I could do it with 4, you see, if you look at these tiles, you see that there's this little funny star-shaped thing there, and 2 of them on here, and there's only one little place where you have a slot for them to go into, and that's this one. So you cut this one out and glue it to that, take another 2 versions of this, glue it on here and here, and you don't need that one. So you could do it with 5. So I went home, and then I started thinking about this, cutting up and seeing whether I could improve on that. And I got it down to 4, and I thought I was quite pleased with that. And then I got it down to 2, and I wasn't so pleased. Now, why wasn't I so pleased? I think the reason that I wasn't so pleased was I thought, God, this is so easy. It must have been known to people. I think that's why I thought that. But I do remember being disappointed when it came down to 2. I rather like my set of 4. But the set of 2 I originally hit on is shown in this picture here, where we have, it's kites and darts. Here we have the kite, and here we have the dart. And those are the only 2. And I have a rule where they've got corners which are either colored black or white, and you have to match the corners. You can do this with knobs and notches if you like. Make a jigsaw puzzle out of it. Well, I'll show you one in a minute. And each one of the kites you have to put lines on in an appropriate way, and each dart you do as well. And I've done that on this side, on the right-hand side, and you will see that it brings out the pattern we just had before with the pentagons. It's just they assemble to make the pentagons, and the dotted ones, the shaded ones, make either the rhombus here, or the jester's cap here, or the pentacle over there. And that is the pattern we just had before. And you can see that if I do it right. And I'm not quite sure which one I need, but let's try that. And probably it's the orange one. Let's try that one. Yeah, I think that's it. So you can see they're really the same kind of pattern, but the kites and darts are done in a way that you don't need so many different tiles, that's all. Now, you can also modify them, as I say, to make a jigsaw puzzle type arrangement. And here's one which is sort of influenced by Escher to some degree, where there are 2 birds, the big bird and the little bird, and the only way you can assemble them as a jigsaw puzzle is in an arrangement like this, which never repeats itself. And you can then go back and see how that ties in with these ones. Well, I hope I can. It wasn't designed to fit this transparency, but I managed to find a place where they fit. And there I think you can see the big birds are the kites, and the little birds are the darts. And that's all they are, but it makes a nice jigsaw puzzle. Okay. Now you can also do 2 in another way, which are actually more commonly used, it turns out, because they're just rhombuses. And the colouring I've got here is you have to match those colours, and it forces this non-periodic arrangement, which I've just been showing you. And what you get, I'll start off by relating it to the kites and darts. There you are. So each dart is drawn, you have the same lines drawn on in each kite the same way, and you end up with this pattern of rhombuses. Now this pattern has been used in all sorts of places. I'll show you some places where it has been used, but often just like this. And I always thought that's a bit disappointing because you don't know why the pattern is like that. You think, well, there are lots of ways of doing rhombuses. You could just make them regular patterns, so why do you do them like this? And you might be saying, well, that's what you're supposed to do, but that's not good enough, is it? But if you have the matching rules, like here, then it does force that type of arrangement. I guess there are a few things I should say about this. One is, okay, I said it forces it, but are there more than one way of doing it? Is there more than one way of doing it? Well, it depends. The answer is both. It's unique, and there's infinitely many different ways of doing it. In fact, 2 to the Aleph naught, the number of points there are on the real line, 2 to the Aleph naught number of different ways of doing it. But they're all the same in a certain sense. If you were given 2 of these patterns and you wanted to see whether they were the same or different, and you could only examine a finite portion, you would never tell. Because any finite portion in one of them will appear in the other one infinitely many times. So as far as finite arrangements are concerned, they're identical. The only differences are way out at infinity, and that's quite a subtle thing. Well, let me not go into the subtleties of that, but it is the case that, strictly speaking, if you go all the way out to infinity, there are all the different ways of doing it. It depends on sort of where you start in the hierarchy, you see. They're all hierarchical in the same way that I started, but you could sort of start in different places, and that makes a difference out at infinity, but as far as finite arrangements are concerned, they're all the same. Okay. Now, these are all the 5-fold ones, or 10-fold. It depends whether you can call them either 5-fold or 10-fold, depending on your rules. I'm not going to make a distinction there. But there are others. And here we have a 12-fold one. That's a rather nice one, made by Galen and Nissen. He's Swiss. I'm not sure whether Galen's Swiss. There was a competition, actually. I thought that the ones that they produced were the nicest ones. These are 12-fold. That's one of them. And they haven't got matching rules, but you can make matching rules. It's a little bit more complicated how to do it. You can't do it with just... I think there are 3 different shapes here, but you have to have another shape to force the matching rule, so it's really a 4-tile thing. And here's another version of the same thing. Really rather nice. There are also the 8-fold ones, which Robert Amann and somebody called Beekner produced. Amann was very rapid. Martin Gardner had an article on these things, and he announced he was going to produce something that he hadn't ever shown before, and I don't think he said very much about what they were like, and Robert Amann rediscovered the rhombus ones, which is very remarkable, I thought, in very less than a month, I suppose. Okay. Now, what do I want to say? Well, sometimes people say, well, you find these things in Islamic patterns, Islamic buildings, and you certainly find a lot of extraordinary looking patterns in Islamic buildings with all sorts of symmetries. Here's a nice example here, and you see this part of the wall. I'm not sure I've counted what these ones are. That's 10-fold, I think, here, and so on. But they're all limited regions, and there's no rule about how you might go out to infinity. Or if you see a nice pattern of these things, it's almost always the case that there's an evident symmetry to it, that it just repeats itself. And so just having interesting symmetries, the symmetries don't extend to the whole pattern, they're just local symmetries. So you can have these local symmetries which are not crystallographic, but the pattern as a whole is a crystallographic thing. One of the more remarkable examples was pointed out by, which way up I'm supposed to do this? No, that's wrong. That's it, yes. Paul Steinhardt and a Chinese chap, I've forgotten his name now. But anyway, they did try and relate it to the tilings that I had. I think there are some relationships, but there's no evidence that there was any kind of a rule that would force non-periodicity. In fact, the examples, like the one up there, you can see it actually is completely periodic. So, and it's less obvious here what's going on. And they have a certain hierarchical aspect. You see they're subdivided, but not in a way that repeats the patterns on the big scale. So it's not clear whether maybe somewhere in some building such an example will actually be found of these non-periodic things, but I want to show you something else which is a bit different. Somewhat later, but not that much later. 1619. These are pictures done under the instruction of Johannes Kepler, the famous astronomer, who discovered the Keplerian orbits, ellipsis, and so on. But he also fiddled around with all sorts of things, and he liked polyhedra and reentrant and how you fill space with different shapes and so on like that. But he had a page in one of his books, Harmonica Mundi, Volume 2, 1619, in which there are all these different, very curious symmetries. Now, my father owned a copy of this book, and I had seen this page some years before finding these patterns which I've just been showing you, but I wasn't thinking about them at the time. But let me show you something. I'm going to concentrate now on this pattern called AA, that one there. Let's make it a bit bigger. There we are. And now I want to show you something. You see, it's made up of pentagons, regular pentagons put together, and then these little holes in them which are decagonal shapes, and these stars, these pentacles. Now, I'm going to try and find the right spot here, which may be a little tricky. Here we are. And look, it fits exactly. Not only does it fit exactly, but in Kepler's picture, he drew an extra little line there for some reason. And that line also fits exactly. Now, what was he doing? I don't know. I really don't know. I was giving a lecture like this somewhere, and somebody in the audience at the end said, yes, there was a letter that Kepler wrote to somebody, and he explained what he was doing in his pictures. I said, oh, that's very interesting. Can you find out and let me know? Well, I heard nothing more from her. Various times I've got people to look at Kepler's letters and things, and the best they could find were letters that he had written to the person who actually did the drawing. So that was he had an artist actually to draw these things for him, but were strictly under his instruction. So they were Kepler's pictures, no doubt. My guess is that he was probably certainly interested in space filling with regular shapes and so on, and crystals. Well, people didn't even know really about atoms in those days, but it was one possibility, and I imagine that the idea of crystals being atoms arranged in a regular way was certainly a strong possibility. And I suspect that Kepler was also interested in living things, and that maybe plants and so on might have had made use of some other symmetries, such as the ones in his pictures here. I have no idea, that's pure speculation. There was a time when people were just finding examples of what were called quasi-crystals, which seemed to have the tenfold, fivefold and tenfold symmetries, and then they seemed to find some eightfold ones. And then I was visiting Switzerland, this chap Nissen, who did one of the pictures I showed you earlier, the 12-fold one. He and a colleague produced these ones. And the reason he was interested in this was that he claimed to have an alloy which produced diffraction patterns which seemed to suggest they were 12-fold symmetry. And nobody seemed to believe him, and he showed me these things, and I thought, well, it looked fairly persuasive. They weren't quite uniform over the whole picture. And then he showed me the little points from the diffraction pattern. These are electrons, you shine electrons on, and they scatter out at particular angles, and then you see the shapes of the little points of light that you get where the electrons hit, and this tells you something of the symmetry. And he showed me this with a 12-fold symmetry, little points. I looked at this, and I started joining them up with little squares of triangles and like that. And I thought, I've seen that picture before somewhere. And I thought, where on earth have I seen that before? And then it dawned on me, here, it's that one. If you put the points of the diffraction pattern on the corners of this arrangement here it is a bit bigger, that's the diffraction pattern. Well, there are probably some other points scattered about, but it was that particular pattern. Again, I have no idea what Kepler was doing. I'm sure he didn't know anything about diffraction patterns, but nevertheless, he had some deep insights in other ways too, so who knows. I'll just leave you that's a bit of a conundrum. Okay, let's do something a little different here, if I can get it to work, which is not necessarily the case. Here we have, I'm afraid it's an old slide, and you'll see they got rather messed up. I must get a new one. But these are rhombuses, which you can probably just about see back there. So it's a nice big pattern of the rhombuses. I can do it with that, can't I? Yeah. I don't need the transparencies. Okay, so that's rhombuses. What's that one? Well, that's rhombuses too, but I think I can't even see them very well from here. I can see those blobs there, but they're little rhombuses. The point about this is that you can put others on top and get nice diffraction patterns. I have to worry about that spot because that's just the light, isn't it? I should probably do, never mind, don't worry about that. I don't know whether I can do this very well here. But you can find a little place where, oh, there, that's good. See if I can get that spot in the middle now. And a nice one. Up there, probably. Yeah, you see those lines? The lines are where they disagree. And where you don't see a line, that's where they agree. Now, this is where I shall probably fail, but let me try it. I've marked a spot where, let's just see, that's not it. I thought I'd marked it. It's hard to see here. Okay. If you get it right, which is hard to do, I'm afraid. I think it's best if I twist it a bit more. That's confusing, that other one. It's not working. Let's try and match my marks, that might help. It's not working very well, is it? There should be just, oh, you can probably just about see it. There's a line right down the middle. And it matches everywhere except along that line. Not very good. I think that's the best I'm going to do. You can probably see the line extending from here to here. That line is where it disagrees. It agrees everywhere else. You see, that's one of these 99.9 things, if I got it right. I think I shouldn't waste too much time on that. It ought to be just about there. I think you just about see it. I should glue them together, and then but of course then the effect isn't. I think that's the best I'm going to be able to do. I'm sorry about it. I think one trouble also is that these machines. Well, I shouldn't blame it on the machine. It's not quite... Oh, did you get it? Ah, there you are. Sorry it took so long. I think perhaps I'll use this other machine. Oh, I have to get it going, don't I? I know how to move the picture, but how do I turn it on? Is it that white? Is it square? No, that's not it. I'm very stupid at these things. Should I be pressing something? Back, front? Oh, it's over there, of course. Perhaps it was there all the time, was it? Yes. Well, you can see this. Actually, it hasn't been put up in the building yet, has it? This is a nice poster did in our old building. I think it's being stored somewhere away, isn't it? Probably. Anyway, it's made up out of little pieces, plastic pieces that were given to me by a mathematician, Ron Graham, and some of them were made by some other people, Michael White and his company, and the big one in the middle is the Ron Graham's one, and they're basically kites and darts with the matching rules done by little knobs and things. And it's also coloured in a very specific way, which the colouring is unique up to permutation of the colours, and it produces some nice things if you sort of squint your eye and look at it. Up on the top left, we see a nice straightforward kites and darts. On the top right, rhombus 1. Bottom left, we see the modification, which gives you the birds and the relationship to the pentagons as well. So it's a little bit baffling. Right in the middle, there is a dog, and the dog is not, it's cheating. He's a different shape from the others. But if you have one dog in there, the tiling is completely unique right out to infinity. So you don't have this business about 2 to the Aleph naught there. It's unique. And the one thing on the right with the diffraction pattern is an actual quasi-crystal. This is an actual material produced by people in Japan. And now you can produce ones that you can actually see. I mean, it's probably only about that big, but you can see it quite clearly. And it's a regular dodecahedron, which is not allowed for a crystal. So it's quite interesting that you can have that. And there's a bigger picture of the actual quasi-crystal. I think they're called crystals now, so I don't know. I think they have so many properties of crystals that people prefer to call them all crystals. I'm not sure whether I like that or not, but never mind. Now, apart from the fact that that's upside down, which maybe shouldn't matter, it's on. I hope they're not all upside down. That is the first time these things were ever used in architectural design. That was anywhere. Well, I hope the others aren't like that. An architectural design on a building. This was the Tokyo Metropolitan University, and the architect there wanted to use kites and darts, so you can probably see them. They're a little bit hidden with having all sorts of other marks on top of them, but kites and darts. And when the thing was assembled, the architect looked at it very carefully, and he found they'd made a mistake, and they had them take it out and put it back correctly, which impressed me a lot. It's completely right, at least as far as I can tell. It's supposed to have some connection with the shape of Tokyo as well, which I don't know much about, but I think it was rather very nicely done. Okay, that's right way up. This is a rather gaudy looking building in Melbourne, I think it is, Australia, in Melbourne, and where they've used kites and darts all over the front and all over inside too, and it's rather an extraordinary place. It's one of the first buildings I know which made use of these things. And you can see up on the top right, I think that's got the stripes on them that I was showing you. But it seemed to be pretty accurately done. Yeah, they've got the stripes on the other ones too, yeah, which you have to match. Now there's a much more sedate version on the ground down here. You see this is just straightforward rhombuses. This is in Stony Brook in Long Island, New York. And that's the mathematics building, and they wanted to use a tiling of this kind, but it's just straightforward rhombuses, as you'll find a lot of. See this again, straightforward rhombuses. This is in Perth, in Australia, and I think this is the Cosmology Centre or something. It's a very nice popular science place in Perth. And they wanted to use the tilings, rhombus tilings on the floor. Perfectly nicely done. I think the biggest area I've ever seen is also in Perth. It is in their chemistry building. And again, it's just straight rhombuses. And here we have kites and darts. This is, I think, in the United States, Carleton University somewhere, yep, which is nicely done. Kites and darts, with also bringing out some pattern with the colouring, which is very attractive. This is the other place, St John's College in Cambridge, and this is the entrance to the building. Well, it's called the Penrose building, and I say it's nothing to do with me whatsoever. Some architect who designed buildings at St John's College in the 19th century, and it was converted to become a library building, and for the entrance they wanted to put this door which swings round. You see, the door is now open so you can go either side. When it's closed, you can only see half the pattern, and the door swings round, and it's kites and darts, perfectly correctly done. And here we have Wadham College, Oxford. This is a pattern which it's just in front of the student bar, and it's usually filled with lots of cigarette stubs and beer stains and so on. But I think it's been reasonably scrubbed down, but not terribly perfectly. And it is matching rules. I was with my wife when they were laying this thing, and I went to a play at the Playhouse, I think, and we came back, and they were just about finishing the laying down, and I thought, well, I'd better have a look and see what they've done. And so I looked at it, and it looked all right, I thought, but a little bit disturbing. And so I went up on a higher level and looked down on it, and I kept thinking, there's something a bit disturbing about that. And then I realized, right at the edge, one of the workmen had seen you could put another tile in, which would fit all right, but it would fit all right there. But if you kept on going, somewhere in the middle of the lawn, you'd find you'd get stuck. So I had to have them pull it out, I'm afraid, and what's there now is correct, but there is this danger because it is a non-local business. Let me move on to... Yes, this is actually a three-dimensional version. This is, I hope, going to appear on a wall. The tiling out front of our building was financed by Andre Stern very generously, and he was having a new building made, and he wanted to have something in there a bit different. So I suggested this three-dimensional version. It's just the rhombuses, but you see that they're all the same size and shape, the rhombuses. It's just the angle that you see them makes either the fat one or the thin one, and it makes this undulating terrain, which is quite nice. And here we have our building. So let me try and say something about this now, because it is the rhombus tiling, but it's got more to it. And I want to describe, I'm afraid I shut this up, didn't I? There is the rhombus tiling, but you see more to it there. There's some patterns there. Now, you may remember that when I was showing the pattern of pentagons and so on, and let's take the bigger version here, you have places where there are these regular decagons, and each time you have a regular decagon, it's surrounded by a ring of 10 pentagons. So I thought maybe you could enhance these rings somewhat by having a circle going around them. So there you are. Now, that, of course, doesn't do the same thing to all the pentagons. So let's do something else. I'm going to complete these things a little bit. See, if I do that, you can see that it's really a sort of fattened up version of here's the pentacle a bit fattened up, and the jester's cap fattened up, and then the pentagons have done funny things at the expense of those. But you can see the relationship to these here, because there's the pentacle. There's the pentacle there, you see. So if I add those extra lines, we sort of retrieved a curvilinear version of the one that we had before. And it would be nice to put those as marks on some actual tilings. And the tilings, the easiest ones to make are the rhombus ones. But if you do that, then you find that the rhombus, some of them are different. You see that rhombus has a different arrangement in the other. So we have to add a few more lines. Here we go. And if you do that, then the fat rhombus, it has everything the same, 2 lines going across each other, and the thin rhombus with 2 lines across. The pattern itself is now just that. Remember what we had first, which was this, or second, then we add a few more lines, and we have that arrangement. And so I was rather hoping that that would be the major feature when you see the tiles, and it was suggested that the tiles should have stainless steel arcs. I thought that sounded really nice. And I remember coming back, I think I was at a conference in Edinburgh or somewhere up north, and there were a set of, I think, 6 tiles in front of the old building, and I came and looked at them, and there seemed to be 2 things wrong with them. One was that the stainless steel arcs didn't seem to join on. I mean, they joined, but some were bright and some were dark, and the reason was that they were apparently what's called combed, and the combing has a different grain to it. So they said, oh, well, we can fix that by polishing instead of combing it. But the other problem was that the tiles looked very different. One was much darker than the other, and that wasn't what I wanted. I wanted them to look fairly similar, so that the pattern of the arcs was what you saw. And then a few days later I came back, and the tiles looked the same. The 2 different rhombuses looked the same as each other. And I thought, that looks much better. Maybe they've got some different tiles. But it wasn't that at all. The reason was the first day I'd seen them, it had been raining, and they were wet. And the second day, it hadn't. It was nice and dry. And so we thought, well, that's nice, because then you get 2 different kinds of pattern. When it's dry, you see mainly the arcs, and when it's wet, you can bring out the other pattern. So I thought that's rather nice. Anyway, here we have the building as a whole, well, from that angle. And here we have a sort of shot in front of the main entrance at the back there. And you can see these rings. That's the ring of pentagons as it was, now changed into a circle. And you have several circles, and you have sort of bigger ones going around. I'm not sure whether you can see it very well here. Maybe the other picture is better for that. Yeah, here we are. Yeah. So you can see, let's just check. I think if you take the circle just up there, and then a little bit further out, you find a sort of floral pattern of a 10-sided shape. So on. I thought it might be amusing just to see, how if you follow the lines. And all. Well, I can give you a conjecture. I don't know if I want to say it's a conjecture or not, because I haven't really thought about it much. But you see, sometimes these patterns always join up in some way. But do they form closed loops? Well, you can see some of them. You see the circle. Okay, that's a closed loop. You sometimes see double circles. Not sure if I can find one there. 2 like that. That's another shape. Or you can see the big curvilinear decagon. And you also find a curvilinear pentagon in the right places, which is something I hadn't quite expected, but you see them too. And so you get closed shapes. But if they cross each other, do you ever get a closed shape? Are those 4 the only ones you ever get? If you find anything which doesn't belong to one of those sets, just sort of by inspection, the only ones I've found I've never been able to close, and they go right off the picture. So a conjecture might be that those are the only closed loops. That may well be false, because I haven't any idea really. This if you want to notice the shape of the tilings, gives you what shape they are. Okay, I think that's all. There are a few other things I can say, but perhaps people have questions, and I'd better leave it at that. I will show that there's one more picture. No. That's just the beginning, isn't it? I thought there was one more picture. Oh, it's got lost. Never mind. No, it just showed what they look like when they're wet. But unless it's after this. No, that's right, at the beginning. One of them's got lost. Never mind. Thank you very much.